Hi everyone, this is the second part of problem solving session. In the second part, we will cover Riemann sums. After solving this question, which is about Riemann sum, we will talk about the geometric meaning of definite integral. And then finally, we will try to understand what is the relation between the area under the curve and the definite integral. So this question is all about how do we use Riemann sum to find the exact area under the curve. Okay, let me emphasize the statement for you. We will find a formula for the Riemann sum obtained by dividing the interval into n equal subintervals. We will use right-hand points, and then we take the limit as n goes to infinity to calculate the exact area under the curve, where n is the number of rectangles. Okay, so this is our expression for the function, and the interval is from 0 to 3. So this is the curve y equals x squared plus 1. I draw a graph for it. And our interval is from 0 to 3. And we will divide this interval into n many subintervals. So I divided it like this. Let's say this is the first subinterval, second subinterval, third, and somewhere here we will have kth subinterval and so on. So how do we construct the rectangles over these subintervals? It is given in the question that we should use right-hand endpoints. So that's how you should create the rectangles. Choose the right-hand point, go up till the curve. This will be the height, and complete your rectangle like this. You will do always the same to construct your rectangles. And let's do once more. This is the right-hand point of the kth subinterval. Go up till the curve. This will be the height, okay? You know, this is the height. F of xk will give you the height of that rectangle. And then you will complete your rectangle like this. You see? This is the area of the kth rectangle. So let's deal with it. Area of kth rectangle. So let's denote it by AK. Okay? And let's try to find an expression for it. Okay, base times height, I will write, right? Okay, this is the height, f of xk times the base. What about the base? You know, the whole length for the interval is 3. And we divide it into how many sub-intervals? N many, right? Because, you know, this is xn. Let's indicate that we divide it into n many sub-intervals. And let's call this expression as delta x. Delta x will be the length of each sub-interval. Delta x, like this, okay? And we also need to compute an expression for the point xk here. This is the kth point. Why do I need it? Because we are computing the height by computing the image of your function at xk. So what is xk? It is in fact the initial point 0 plus how many delta x's we need to move to reach xk. In fact, we add k many delta x's to hit the point xk. So the formula for xk is k times 3 over n, so 3k over n. Okay, so let's also put xk here. This is the expression for the area of the kth rectangle. So it is given by f of xk being 3k over n times delta x. Delta x is 3 over n, the length of each subinterval. Okay, after finding the area of the kth rectangle like this, now I can write an expression for the sum of the areas. Sum of the areas of n rectangles. Okay. I will be using sigma notation for it because we have how many rectangles and many rectangles, and for each rectangle AK is the area of it. So this expression goes like K is runs 1 to n, and the expression for AK is height times base. So let's try to find out. XK is given by 3K over n. Delta X is given by 3 over n. Now, it is time to compute the image of function f at this point, 3K over n. Do you remember your function? Our function is this one, f of x squared plus 1. So, it is in fact 3K over n squared plus 1. This is the image of your function at that given point, times 3 over n. Okay, now the rest is just computation, okay? Compute this square and then we will multiply it with 3 over n. So what we have here is k is from 1 to n, 9k square over n square plus 1 times 3 over n. So let me write the multiplied version. 3 over n, 3 over n, right? That's what we have inside the sigma notation. And then it is time to distribute the sigma notation over sum. That's why we studied how to play with sigma notation in the previous lecture, because we needed to construct Riemann sums. By the way, this expression here is called as the Riemann sum. Okay? Riemann sum means the sum of the areas of n rectangles in this form. Okay, so let's move on with the computation. Let's distribute the summation over sum. That's what we were doing. K is from 1 to n, 9k squared over n squared, 3 over n plus another summation from k and 3 over n. Okay, now for the first one, you know, there is a constant there. This is a constant, right? Which can go out from the sigma notation. So we have 3 of, also, sorry, maybe I should write the multiplied version here. Let me write the multiplied version. Here, but we have 27 k squared over n cubed. That's why this whole thing is the constant which should go out. 27 over n cubed. We have k squared and 3 over n again. This is a constant which should go out. K is from 1 to n, just 1. Okay, what do we have now? 27 over n cubed, sum of squares from k1 to n. There is a formula for it. What was that? n plus 1, 2n plus 1 over 6. This is the formula for sum of squares. And the second part, 3 over n. So you are summing up ones, how many times? N times. So this should be just n, right? Okay, so the result for this sigma notation is, we have simplifications, of course. Divide by 3. Simplify these, and what we have at the end is 9, n plus 1, 2n plus 1 divided by 2n squared plus 3. Okay, this is what? Let's remember what we were doing. This is the sum of the areas of the n rectangles. Let's denote it by S, not k, but n, because look at the result. It depends on n. Okay, let's call it as Sn. Okay, now this is the sum of the areas of n rectangles. Now I will try to relate this expression to the exact area under the curve. How do you relate these two? First of all, the exact area under the curve is the same as the definite integral of the given function over the given interval. Remember, the given interval was from 0 to 3. Okay, then the definite integral is the same as the exact area under the curve. Under the curve, right? And this exact area is somehow related to the sum of the areas, right? K is from 1 to n, AK. These are the sum of the areas of rectangles, which I denote by Sn. Are they the same? These two. Are they the same? These two. No, they are not the same. Look at your picture. We have errors. The sum of the areas of the rectangles gives you some bigger value than the exact area. You see they are exceeding the exact area over the yellow shaded parts. So the exact area under the curve is not the same as the sum of the areas of the rectangles. But how can I make them the same? The more rectangles you have, the less error you obtain, right? So the number of rectangles, if I send this number n, the number of rectangles, to infinity, then there will be no errors anymore. The sum of the rectangles, infinitely many rectangles, will cover the exact area under the curve, okay? That's the idea. So once you put the limit notation here as n goes to infinity, this is very important. Only then you find the exact area under the curve. So what we should do is to compute the limit as n goes to n of the expression that we find for Sn. So Sn is here. Let's write the expression for it. Here it is 9 n plus 1 to n plus 1 divided by 2n squared plus 3. Okay, if we can compute this limit, that number will be the exact area under the curve. At the same time, will be the result of the definite integral. How do you compute this limit? N goes to infinity. Let me write down the expression. If we multiply these polynomials, so it is 9 times 2n squared plus 3n plus 1 divided by 2n squared plus 3. Okay, I just do this multiplication. And now if you concentrate on the degrees are equal. Then the limit is the ratio of the coefficients, right? So the result of the limit is 9 times 2 over 2. So you see I am taking the ratio of the coefficients. Also plus 3 is there as a constant. So the result is 12. Okay? So what is this positive real number 12? It is the exact area under the curve. And at the same time, it is the result of the definite integral. And how do we obtain it? By taking the limit as n goes to infinity of the Riemann sum, okay? So that's it. Let me also write one more expression, which is the Riemann sum. So what is the expression for AK? It is height times the base. So this is what we call as the Riemann sum, if you like. And if you take the limit as n goes to infinity of the Riemann sum, you find the exact value of the definite integral. In other words, you find the exact area under the curve. Okay, so that's a very nice question, summarizing you everything about Riemann sum, how we construct it and how we use it to find the exact area. And and what is the relation between the definite integral and the Riemann sum? Here it is given, right? Any questions? If not, let me move forward. This group of questions helps us to understand the relation between the definite integral and the geometric meaning of it. Okay, let me try to explain while solving the examples. Here we have a definite integral like that. Okay. If we don't know any integration rules yet, right? We cannot find the result by using the integration rules yet. Next week, we will start covering the integration rules, but this time we don't know them yet. But we can still find the result of this definite integral because we know the geometric meaning of it. What is that? This is the area, exact area under the curve y equals 9 minus x squared square root. So if we can draw the graph of this curve, then if there is a way to find the area under this graph, we can find the result of this definite integral. So we should concentrate on this geometric meaning of the definite integral. So let's see how we can graph it. This is y equals 9 minus x squared square root. If you take the square of both sides and rewrite this curve, you will recognize it as a circle of radius 3, right? This is the equation of circle of radius 3. And if you solve for y from this equation again, it is in fact plus minus like that. And what does it mean to choose plus? Let me explain this part. Let's first draw the circle of radius 3 like this. As you see, this circle have two parts, upper half and the lower half. Over this upper half, you should notice that all the y components of the points are positive. That's why the upper half of the circle has this equation, while the lower part will have the equation with the minus sign. Why there should be a minus sign in front of this equation for the lower part? Because over the lower part, over this part, lower curve, all the y components gets negative values. That's why there should be this negative sign in front of the expression. So you see, what we are interested in for this definite integral is this curve, the upper half of the circle of radius 3. Okay, so the exact area that we talk about here is this part, okay? The definite integral in this example is given by the half of the area of this disk. So let's write this down. So we want to compute this definite integral from minus 3 to 3, 9 minus x squared dx. So what is this curve? I just explained why we should just draw the upper part of the circle for this curve, because it is positive. Okay, so this is the circle of radius 3. That's why from minus 3 to 3. And these are, in fact, the upper-lower bounds of the definite integral. So the geometric meaning of this definite integral is what? Is the area under the given curve. Nine minus x squared square root, whose graph looks like this. So we should compute this area, right? And we know how to compute the area of the circle. How we can do that? Pi r squared. I need to take the half of it because this is half circle. So the result is 9 pi over 2. You see? Without using any integration formulas, we were able to compute the result of this definite integral. How? By using the geometric meaning of it. Okay, that's it. Okay, let's choose another question from this group. For example, 20. Now, let's try to understand this definite integral. Let's try to compute it by using the geometric meaning of it. This is the question now. All we need to do is to draw a graph for this y function, right? If we can draw the graph, then we can try to find the area under it. So let's start by drawing the graph for absolute sine of x. You know, this is y equals x. What if we take all the negative values to the positive part by taking the symmetric of it? Then you will obtain the graph for absolute sine x, like that. And you see there is this plus 1 here. So by shifting, we can obtain the graph of 1 minus absolute sine x. By the way, if we reverse the graph, that will correspond minus absolute sine x, okay? Let me draw it in colors. So this is y equals minus absolute sine x because I just reversed the graph. This is what we should do if we multiply everything with -1. And then we should do one more shifting. If you take that pink graph 1 units up, that will correspond to the graph of this curve, 1 minus absolute sine. You see, I moved this graph 1 units up so that it will hit 1 here. Also, you can easily find these intercepts. So, for what values of x the image becomes 0? What are those values? Of course, -1 and +1. You can easily detect that. So this is the graph of the desired curve, and the result of this definite integral is area of that triangle under the curve. Which triangle I mean? This triangle, okay? Area of the triangle. So you can compute it, right? Base times height divided by 2. So base is 2, height is 1 divided by 2. So the result of this definite integral is computed as 1 by using the graph of the curve y equals 1 minus absolute sine of x. Okay? Any questions? I think these two examples gives you everything to understand the relation between definite integral and the area under the curve. So every definite integral has a geometric meaning. It is the same as the area under the curve. The curve being the function written inside the integral, okay? So that's it. If no questions, I want to move on with the next part. The next part is about the average value of f. This is just a recall for you from the lecture notes. Recall. So the average value of f is computed by this formula. The definite integral divided by the length of the interval, okay? Like that. So let's try to find the average value given in 60. This is a straightforward question, okay? F of x is x squared minus f of t. T is the variable. F of t is t squared minus t. And the interval is given from -2 to 1. And we want to compute f average. So you will compute this definite integral from -2 to 1 of this function divided by the length of the interval, which is computed like this. So what we should compute is this definite integral from -2 to 1 divided by 3. Okay, that's what we should compute now. And now, for the first time, we will start using antiderivatives to find the result of definite integrals. So far, how did we compute definite integrals? Here, by using the geometric meaning of it. We didn't use any antiderivative formula, but starting from this example on, we will use antiderivatives to find the result of the integrals. I have a recall for you about this part. Consider x to the power n, the most general exponential function, okay? You know, taking derivative and antiderivative are inverse operations. They are doing the inverse things to your function. So tell me a function now whose derivative is x to the power n. So you should think in the reverse order. We are searching for a power function whose derivative is x to the power n. First of all, since we are subtracting 1 from the power while taking the derivative, I should start by writing x to the power n plus 1, right? Why I write it like that? Because if I take the derivative of x to the power n plus 1 will come down. And then you will subtract 1 from the power to obtain x to the power n. But what about this extra coefficient now? I need to get rid of it. How can I get rid of it? Of course, by putting 1 over that coefficient in front, right? Now, if you take the derivative of this expression, you will obtain this. And similarly, if you consider, if you ask yourself, what is the antiderivative of x to the power n? You need to tell this. Okay, derivative and antiderivative are inverse operations. Okay, now, antiderivative is the same as taking integral. From now on, instead of saying antiderivative, we can say integral of x to the power n. And there is a notation for it. So from now on, instead of saying antiderivative, I will be using integral notation. What do I mean is, so integral notation, you know, integral of x to the power n is like that. This is the first time that I wrote an integration formula on your template, okay? So first integration formula is this one for power function. You add 1 to the power and you divide by the same power. By the way, you should assume that n is different than 1 because you don't want to put 0 to the denominator. If n equals minus 1, there is another rule which we will cover next week, okay? Then you will understand what happens if n equals minus 1 next week. But for all the values of n different than minus 1, you can use this rule as the integration rule of it. And what if your integral is a definite integral like this with boundaries? Then this happens. Okay, you apply your rule, you add 1 to the power, divide by the same power, and then you need to put this notation from x equals a to b. What does this notation mean? It means that you first insert b and then a for your x, okay? So like that. Insert b for x, insert a for x, and then you will take the difference. That notation means that whenever you have a definite integral and whenever you know the integration rule, you need to compute it like this. Okay, after all those recalls, now we can turn back to our example. What we were trying to compute here is this definite integral from minus 2 to 1, t square minus t dt. Okay, use your rule. Add 1 to the power, divide by the same power. This is the antiderivative of t squared. Again, add 1 to the power, divide by the same power. Antiderivative of t is t squared over 2. We have boundaries. Be careful. You need to put them here. From t equals 1 to t equals minus 2. What does this notation mean? You first insert 1 to your t, and then you insert the lower bound for your t, which is minus 2. Okay, and then you will take the difference of these two. So we first insert upper bound for our function, lower bound, and then we take the difference. And if you do this computation, you will find 3 over 2 as the result, okay? So the average value of the given function is 3 over 2 over 3, okay? So that will be the result. Is that okay? Sorry, wait. The overall result is 3 over 2. That's why this integral is I guess 9 over 2. Okay, the result of this computation. Okay, so that's it. I think the average value formula is not that, I mean, the core part of this example is how to compute this part, okay? This is the first time that we compute a definite integral by using the formula, and it is computed here. You think of the antiderivatives of the given polynomials, like that. And the general formula works like this here. I gave you the general formula, right? Okay, any questions? Let's move on to the last example. This will be the last example for today, which I think is very useful to understand the content. This is a very nice example that requires critical thinking. That's why I want you to listen to me really carefully. What is the question? For what values of a and b, the value of this integral is minimum? So we want to search for the values of the parameters a and b that minimizes the value of this integral. Okay, how can we proceed? There are two ways to go. Either we will compute the integral algebraically by using the integration rule that I just mentioned, or we will use the geometric meaning of the definite integral. One of them should work. Let's start with the algebraic computation. Okay, how do you compute this definite integral? You add 1 to the power, divide by the same power. This is the antiderivative of x to the power 4, right? Minus 2 is a coefficient, it is constant, it stays there, and then antiderivative of x squared is this. This is we take the integral, and then now it is time to insert the upper lower bounds from x a to b. Now insert your boundaries. B, A. This is b to the power 5, b cubed over 3. I inserted b minus a to the power 5 over 5, a cubed over 3. There is this 2 coefficient here, and then I take the difference. That's how it should be computed, right? Algebraically. Okay, this is the result. What we want to do? We want to find the values of a and b that will minimize this expression. How can you do that? Look at your expression, please. Can you optimize it in terms of the values a and b? The optimization is the content of the last week. What kind of functions you were optimizing in your last homework? All of the functions that we study this semester for optimization problems are single-valued functions. Like they depend on just one variable, f of x. Right? Single-valued functions can be optimized in Calculus 1 course. Single-valued functions, we can optimize this in Calculus 1 course. But look at our function. This function depends on how many variables? It depends on 2 different variables, both a and b. So that's the problem. This function depends on 2 variables, not just single one. It has 2 different parameters inside. That's why we cannot optimize it by using Calculus 1 course, by using the techniques that we covered last week. If it would be depending just b or just a, you would take the first derivative of it, find the critical points, and then you can prove easily whether that critical points gives you maximum or minimum. This is what we were doing during last week, during your last homework, right? How you are optimizing single-valued functions. You take the first derivative, find the critical point, let's say x0, and constructing a sign table for x0, your function you can understand your function takes its minimum value at that critical point. That was the technique that we use to optimize single-valued functions, but we cannot use all those ideas here because our function does not depend on single variable. That's why we need to change our strategy. The algebraic way of computing definite integral gives us a multivariable function so that I can use the technique. I cannot use the usual techniques to find its minimum. That's why we will change our strategy to the second way. Let's use the geometric way of computing definite integral. So we should use geometric meaning of definite integral. Okay, so what about the geometric meaning then? X to the power 4 minus 2x squared dx. The result of this integral is what? Is the area under, it is the total area under the curve. Let me recall something before we start that part. Recall area under the curve and the definite integral, how they are related. I want to recall that to you. Let's say your function looks like this, f of x, okay? And let's say you are trying to compute the definite integral of your function from a to b. How do you relate this definite integral to this area A? So this is exactly the area under your curve, right? A. What if your function behaves like this? Okay. What if it has also negative parts? Then its definite integral from a to b, how this definite integral is related to these areas lying between your curve and x-axis. Let's name this part as A1, A2, A3. How do you relate in this case the definite integral of your function and the areas under the curve? So negative parts will contribute negatively to your integral, okay? Meaning that, you know, this is the negative part, this is the negative part of your function. That's why I need to put an extra minus sign in front of the area. So in this case, the definite integral is not the sum of A1, A2, A3, no. Negative parts contributes negatively, like this one and this one here, to your integral. Okay, this is something important. And this is also explained in the recorded lecture videos in a very detailed way. Now we will use these ideas for our function. Okay, so we need to draw a general sketch for this function. We need to draw the graph of it roughly. So how do we construct a general graph for it? Of course, we will take the first derivative, x cubed for x, we will find critical points, we will find increasing, decreasing intervals, and so on. Let's do this part quickly. X squared minus 1. So what about the critical points then? They are 0, plus, and minus 1. And then you can construct the sign table, right? Because we need the sign table to understand where our function is increasing, where it is decreasing. So minus 1, 0, 1, y prime. If you pick up some values over these intervals like before minus 1, you can pick minus 2, insert to your first derivative function, and you can see whether it is positive or negative. Before minus 1, it takes negative values. Between minus 1 and 0 over this interval, it will take positive values, negative, positive, okay? You can just pick some values and insert to your first derivative function to see those signs. And then, what does this mean about the function itself? Why? So we can understand that over this interval, the original function y is decreasing. Between minus 1 and 0, it is increasing. 0 to 1 decreasing, 1 to infinity increasing. Okay? And we also It will be also useful for us to see the intercept points of this function. This is the original function. I want to understand x-intercepts of it. So you can take the parentheses x squared minus 2 is 0. So you see the intercepts. It is 0 plus minus square root 2. Okay, you see I am not completing the sign table with all the details. I just need to see the graph of it roughly. Yeah, I mean the general sketch, very quick sketch. So let me draw it by just looking at where it is increasing, where it is decreasing, and the intercept points of it. X equals 0, x equals minus square root 2, and x equals plus square root 2. These are the intercepts. And I also know that our function is decreasing from minus infinity to minus 1. Let me also indicate point minus 1 and plus 1 here. Okay, so it will be something like this, I guess, and then after minus 1, it will start increasing. Between 0 and plus 1, it is decreasing. After plus 1, it is increasing again, and it has to intersect x's at plus square root 2. So something like this. I know this is not a perfect graph, not a very detailed one, but it will work. This is a general sketch of the graph of our function like this. So this is generally the graph of y function, which is given as this. Sorry, this is not the expression. It is x to the power 4 minus 2x squared. Okay, so we want to understand this definite integral. Now, we are very close to the result. I will sum up in a minute. Okay, where to put a and where to put b so that this definite integral becomes as small as possible, right? So remember the geometric meaning of this definite integral. You know, I explain it here. The negative parts contributes negatively. So if I put a here and b here somewhere, some points, I don't know what they are now. I am just trying to understand for what values of a and b this definite integral becomes smallest. So if a is there, b is there, then I can shade these parts to understand the result of the definite integral, right? These green shaded parts will help me to understand the result of this. Let's call this part as A1, this part as A2. Let's name this A3 and A4. The result of the definite integral will be A1 plus A2. Sorry, since these are negative parts, I need to put minus sign in front of them, right? And then plus A3 plus A4. These are the positive parts. What we want now? Okay, this is the key point. Key part. We want this result to be as small as possible. So we can move A and B such that we don't know how to choose them yet, but now we start to understand. We can choose A and B such that this part becomes as small as possible, right? That's why we should eliminate these positive contributions. They are positive. They are making the result like more bigger. But we want the smallest possible value. The smallest value we want. So the smallest value of this definite integral can only come from this, only these two negative contributions. This is the smallest value of the integral. By adding A3 and A4, we are just making it bigger. That's why we should choose A and B so that we eliminate these positive contributions. So how to choose A and B then? We should move A to this point minus square root 2 and B to this point plus square root 2. Only then there won't be any positive contributions, right? And only then we will just take the negative part that will make the result as small as possible. So that's my explanation. we should eliminate positive contributions to the result. We should just take negative parts to make the result as small as possible. So, okay, let me remove the question mark. So, this is the only part that we should take. Smallest. Value comes from this. So, A should be chosen as minus square root 2 and B should be chosen as plus square root 2. Let me draw a new picture so that you see completely what happens then. Our graph is roughly like that. If you choose A as this number, minus square root 2, and if you choose B as this number plus square root 2, then what happens to the definite integral? A to B, our function was x to the power 4 2x squared dx. Then the result of this definite integral will only come from these two negative parts. Remember? I called this part as A1 and A2. So minus A1 minus A2. And this is the possible smallest value of the integral. And they happen when you choose, this happens when you choose A as minus square root 2, B as plus square root 2, because for all the other cases, if you choose A over here, B over here, you just add things to your result. It is not smallest anymore. If you choose A here, B here, then okay, it is again negative, but you make the negative part smaller. That's why the required numbers are here and here. So I put the required explanation. Any questions? Only in this case, when A is minus square root 2 and B is plus square root 2, the result of your integral becomes smallest. Why it becomes smallest? Because only in this case, only like that, you can eliminate these positive contributions coming from here and here. You don't want these positive parts. That's why you want to move A here and want to move B here to get rid of these positive additions. And that's it. Oh, okay, so any questions? This was the last example. For this example, I wrote too many things. First, we tried the algebraic way of computing integral, which is using the integration rule. But then we see that the result depends on two variables. Since it is not a single variable function, you cannot apply the techniques that we covered last week. Only if your function would be only if your function is a single variable function, then you can use the optimization technique that we covered last week, which goes like, take the first derivative, find the critical points, draw the sign table to find whether it is maximum or minimum. But this technique is not working here, as your function is not a single variable function. It depends on A and B, two variables. That's why we move to the geometric, we change our strategy and start using the geometric meaning of the definite integral. What is the geometric meaning? The definite integral, which is given here, can be computed also geometrically by using the areas under your curves. Negative parts will contribute negatively, positive parts will contribute positively. To get rid of all positive additions, you need to choose A and B such that you just take the negative part. That's why A should be chosen as minus square root 2 and B should be chosen as plus square root 3. Only then you just cover this whole negative part so that your result becomes smallest. minimum, okay? So that's it. Any questions? Okay, then. Thank you for your attention. I will see you next week. Goodbye.